Hello, everyone. I'm Pia Cortes-Zuleta. I'm a PhD student at LAM under the supervision of Isabel Boas. So today I'm going to present you one of the first results of this synergy program between SOPHIE and SPIRU. So I would like to start explaining, very briefly, why it's important to characterize stellar activity when we want to discover exoplanets around M-dwarfs. So M-dwarfs are active stars. They hold magnetic fields that are the generators of all the phenomena that we know as stellar activity. So the features over the stellar surface are co-rotating with the star, and at the end, they will produce periodic variations in the radial velocities. This can easily lead to false detection of exoplanets. So in this very nice example, we can see how the features over the surface of the sun are modulating the radial velocities and also the activity indicators. In this case, we have the bisector and the full width half maximum. So we have this synergy program between SOPHIE and SPIRU. SOPHIE is an optical spectrograph that is located at OHP here in France. And SPIRU, I hope you already know what it is and what it is. So the idea is that we have around 14 early to mid-late M-dwarfs that we are trying to observe quasi-simultaneously with both instruments to improve the characterization of stellar activity. Why we want to observe in the optical and in the near infrared at the same time? Because when we move towards the near infrared, the temperature contrast will decrease, and this will, at the end, will produce less variations in the radial velocity. That's why we want to observe M-dwarfs in the near infrared. However, we have another issue in the near infrared. It's the Semen effect. So we have a magnetic field, and we have longer wavelengths. So at the end, we will have an increase also in the variations in the radial velocity because of Semen. So we have these two effects that we would like to measure and characterize. I cannot use this. So this works. So we already saw this in previous presentations. AD Leo is one of the first cases that we have in this program. It was proposed a planet around this star. However, it was proposed with optical data. When you observe AD Leo in the near infrared, the proposed signal disappears. So in purple, we have the optical with SOPHIE, and in red, we have SPIRU. So with this, basically, we are saying that the periodic signal that was observed is due to stellar activity and not a planet. So we have this other target, Gliese 205. It's an early M-dwarf. And if we try to find Gliese 205 in this diagram, is here. The size of the marker indicates the strength of the magnetic field. So it's not a really, it's not a star with a really strong magnetic field, and it has a relatively long period. So we derived the stellar parameters using SPIRU and SOPHIE spectra. And if you want to know more about how we derive the parameters of this star, please check out Paul Christofari's poster. So about the rotational period, we know that it's between this range because it has been observed in the past by Harps, Harps-Paul, Narval. However, the periods that were proposed are not the same, and they have this, they are within this range. And also it was proposed hints of differential rotation that at that time, Ebrard et al. 2016, in this work, they couldn't confirm this, but they proposed some hints. And about planets. So there are 2 planet candidates that we are going to kill. So we started taking the SPIRU spectropolarimetry data to measure the longitudinal magnetic field. We rely on the longitudinal magnetic field to constrain the rotational period. So we apply a Gaussian process regression with a quasi-periodic kernel, and we obtain a very good measure of the rotational period. We apply Semen Doppler imaging to construct the large-scale magnetic field over 3 seasons. The 3 seasons are marked in gray here. And when we applied ZDI, we were able also to confirm the differential rotation that was proposed in the past. So now we have values of the rotation for the equator, that is faster, and the pole of this star. We have seen a lot of these maps today. So we have the 3 seasons of observations for this star. We can see that the strength of the magnetic field is decreasing towards the beginning of 2022. We start with a poloidal magnetic field, but we ended up with a dominantly toroidal magnetic field at the beginning of 2022. Something that we notice is that our first season of observations that are at the end of 2019 are in completely agreement with the ones that measured Ebrard et al. In 2016. However, keep in mind that the observations of this work were done in 2013, 2014. So what happened in these 5 years, we don't know, but the magnetic field that we measure are in agreement after 5 years. Now the radial velocities. So in blue are the radial velocities of SOPHIE, and in red the SPIRU. We see that they are not really different. They are following more or less the same patterns. We observe similar scatter in the radial velocities that is different from what we observe in ADLIO. And we observe a similar amplitude of the covariance when we try to apply a GP in these radial velocities. However, this is expected for early M-dwarfs. If we look at the periodogram, we have a nice peak at the expected rotational period. So we computed several activity indicators in the optical dataset and in the near infrared dataset. Before looking at the periodogram, something that we need to keep in mind, and we have differential rotation and we have inclination of the star, is that probably in the periodograms, we won't see one peak exactly at the rotational period that we are expecting, because the features over the stellar surface will be rotating at different velocities. So we need to keep in mind that. So that's why in the periodograms, that I don't know if you can see it, but there is a light green range. This range is indicating the range of the differential rotation. So what we observe in these periodograms is that for SOPHIE, the only activity indicator that is showing a peak close to the rotational period is H alpha, which is expected for M-dwarfs. And in the SPIRU one, we have the full width Hall maximum with a very nice peak at the rotational period. We also tried in the near infrared domain new spectral lines that could be used. We are testing them if we can use them as tracers of activity indicators. So we tested aluminum, titanium, potassium, and iron. And something that is interesting is that the peaks in the periodogram of the aluminum lines are within the range of the differential rotation. So we cannot say much because it's only one star, but it will be really interesting to test this line for more M-dwarfs that we know that they have differential rotation. Next step is to try to filter stellar activity using these activity indicators that we know that are showing some peaks close to the rotational period. So we apply a multidimensional GP framework that it's basically you use one Gaussian process in several time series. So they are all sharing the hyperparameters, in this case, the period, but with different amplitudes. So it was proposed in 2015 by Raxpol with the idea to use the radial velocities, the log RHK, and the bisector. In this case, we replace the log RHK to H alpha in the SOPHIE dataset. And we also use the bisector. And what you can see here is that the radial velocities are basically modulated by activity. If you check the residuals of the radial velocity after this model, we obtain something like 2.9 meters per second. In the case of SPIRU, we don't have an analogous of the bisector, so we only use the full width Hall maximum. And again, we see how the radial velocities are modulated more or less at the same way than the activity indicators. And again, if we check the residuals after this model of the radial velocities, we obtain around 3 meters per second. Now, we can use this very straightforward technique to look if there are Keplerian left in this signal. So we check the periodograms, and there are no other significant peak in these periodograms. So you can interpret this as there is no planet, or maybe the GPs are absorbing the Keplerians. So this is a big debate that we have in the community. How flexible are the Gaussian processes when we are looking for planets and in the presence of stellar activity? But as this GP is learning from the activity indicators, we can confirm that there is no Keplerian left. So in another side of this work, as I told you, we are looking for more near infrared spectral lines that we could use to trace stellar activity. So far we tested aluminum, potassium, iron, and titanium. But from the line-by-line framework that Etienne presented a few hours ago, we have thousands of lines that we could test to see if they are tracing activity or not. So we also took a very, very small sample of M-dwarfs in the SPIRU, around 10 M-dwarfs, to see the periodicities of the lines. And what we see is that potassium tends to show 2 times the rotational period, but however, iron shows results very close to the expected rotational period, and we know that iron is sensitive to activity. So
2 minutes left.
Yes, I'm finishing. So the ideas that I wanted to share with you is that first we have this program between SOPHIE and SPIRU to do a multi-wavelength characterization of M-dwarfs. Why it's important? Because with this, as we have shown you, is that we can confirm or reject exoplanets. In the case of AD Leo and Gliese 205, we rejected planets. Why we see this difference between AD Leo and Gliese 205? Well, they are different stars. They are different. They have different spectral types. AD Leo is a late M-dwarf. They have different magnetic fields. AD Leo has several times the magnetic field of Gliese 205. So it's not really a surprise that we are not seeing the same behavior in the optical and the near infrared. We need to also take into account differential rotation when we want to look for the rotational period of M-dwarfs. It's very useful to use the information from the activity indicators, in this case using a multidimensional GP. And we are extending this work in more M-dwarfs and more spectral lines. So stay tuned for the paper. I hope it will be out soon. And thank you.
Thank you very much, Pia. You really extracted all the data from this target, so you now have 50 more from the WP1.
Okay.
You can go on. Questions? No questions, and online? No questions either. Okay, so let's thank again Pia and all the speakers of the session.